Okay, this is going to be a sort of a tutorial, if you will, on heat, and this is kind of a tough one. Okay, so I'm just going to be straight with you up front. So one of the things that we'll be doing here is trying to give a conceptual basis for the idea of heat. So first of all, heat and temperature are not the same. Temperature is just the average kinetic energy of the system. Think of it as how fast the system's moving. Heat is a form of energy, and it has to flow from an area of hotter to colder. And whenever there's energy involved, energy is work through a distance. And the idea with work through a distance is that something has to be moving. So with that in mind, let's just go over a couple concepts here with the idea of heat. Now we're going to start off with a metaphor, and there's always, metaphors always break down at some point. But the number one thing I'm going to show you on this handout here, which I want you to focus on, is how we can talk about energy. There are a couple different ways. Number one, thermal energy, or ETH. So that's one of the ways I just want you to get it, which is like right here. Okay, so thermal energy. This is kind of a key in that it's energy stored by moving particles. Okay, so the particles have to be moving, and typically one of the things we rely on a lot for an indication of thermal energy is sort of like, for lack of a better term, is a change in temperature. Phase energy is the energy due to the phase of a system. It's either a solid, liquid, or gas. Generally speaking, solids will have the lowest potential energy. Liquids are at a greater potential, and gases are at a far greater potential stored energy, and we'll see that in a minute. And then finally, chemical energy. And I don't ever want to say that it's due to these attractions, but it's not chemical energy. We don't store energy in bonds. That's where the metaphor breaks down. It's when we break bonds, energy goes into the system. When bonds are formed, energy leaves the system. So we kind of have to be careful how we see this. The thing I like about this reading is they really do a little nice job on the history. They also mention too that it involves as far as the storage goes, they kind of compare it to money in different savings accounts, and that's one of the ways that we can think of this energy. Okay, so first, let's talk about the phase energy. So here I have a system in Adam Smith, which hopefully you can see here. And right now, this would look like a solid. So it's water, pretty much as a solid. I'm going to hopefully get this going here, and as it starts to move, it's still water, pretty much as a solid. It's right down by 273. But even then, as I start to heat this up, one of the things that you'll notice, we can still have it as a solid. It's now getting a little closer together, so it's overcoming those forces. It's going more toward a liquid, and then it goes off into a gas. Now, the potential energy over here is huge because it takes a lot of energy to pull these apart to overcome the hydrogen bonds. So the potential for these to come together and give off a bunch of energy is great when they're a gas. That's why gases have the greatest potential energy in a system. Liquids are a little lower in potential energy. And then finally, the solids are have the lowest amount of potential energy. A temperature probe only tells us the kinetic energy. It doesn't tell us the phase. That's what we have to see for ourselves. So let's talk about how we could represent these. And probably one of the best ways to do this would be through a bar chart. So for instance, one of the things we'll see here, the first thing we do is we say, hey, here's a cup of coffee. It's just going to sit out on a desk and cool. Number one, determine the system. It's a cup of coffee. If you notice here, this part right here, and it's hard for me to click on at the same time, but this part with the energy due to the chemical bonds, those don't change. We won't worry about those. The phase stays the same. Again, the phase of a liquid cooling is a liquid cooling. It's the thermal energy that's going to change. So what's going to happen? Well, in this case, you start with the coffee. You end with coffee. The particles aren't rearranged to form a new substance. We can ignore the chemical energy. Next, again, we're dealing with a liquid before and after. So we'll say a liquid, as far as energy goes, has about 2 bars. Take a look. There's the phase change. And as you can see, the phase change, there's no phase change. That hasn't changed. But what has changed? This gets us down to the thermal energy. And now, as you can see, going from here to here, the thermal energy has changed. It's gotten colder. It's the energy due to the motion of the particles. How did it get colder to 2 bars? Where did it go? Hey, it left the system. So to show that, we go to this one. And if you notice, there are 2 bars here. They're not over here. Where are they? They're here. And why is it that we use Q? Well, H for heat and E for energy were taken already. So we're going to use Q for this thing of like enthalpy or heat energy. This is the heat energy that leaves the system. So let's do another example. What if we have a phase change? Tray of ice cubes, minus 8 degrees Celsius is placed on a counter, and it becomes water. What do we know about this? Okay, so the system is the tray of ice cubes. The solid doesn't change the chemical of the water. Like we don't break the bonds within the water molecule. The phase change, it's going to increase the energy because we said liquids have, it takes more to overcome those forces. They're at a greater potential based on their position as a liquid and a solid. And the thermal energy increases because the temperature has to go up. So let's see how we would do this as a bar graph. So to show this, here's what we wind up with. Again, notice thermally the ice is very cold. We've identified the ice here. Thermal is very, very cold, and the phase change saying it's a solid. Now it's going to go from, first of all, it has to warm up to get to 0 degrees, so it can undergo a phase change. If it undergoes a phase change of a solid at 0 to ice at 0, or to water at 0, that has to go up. If you look here, again, we're now at a liquid, and it went from -8 to 0 degrees. So where did it go? It came from outside the system, and it went in. Okay, so if we were to show that, there it is. Okay, so here's the Q. Now, in our example, what we did, the Q here came from water. Okay, it came from warm water. Now, you're going to have to read your lab. They're going to give you some really important information in that lab. And in the lab, the Q, the heat from the water, left the warm water. It got colder. It went into the ice. Again, from a solid to a liquid, the potential energy is different because of the position of those particles. We need to find out what Q is. Do we have the mass of, do we have the specific heat of the warm water? Yes. The amount of energy required to get 1 gram to change 1 degree Celsius. Do we have the change in temperature of that water? Yes. If it's of the warm water and it's going from the warm water, therefore the last part here is the mass. And it's the mass of the warm water. It is not the mass of the ice. Okay, it's doing work on that ice, but it's the mass of the warm water. Those are the 3 things from Q that goes into that ice. Therefore, we're assuming it was all self-contained, and we know exactly how much Q it took to measure a certain amount of ice. That's the goal. If you have any questions, let me know. I would strongly encourage you to do the problems because they'll be of huge help.